Good morning, everybody. On last lecture, we discussed probability theory with you. And today, we are going to start talking about medical statistics, how I said on last lecture. And as usual, we will begin with a definition. What statistics are? What is about statistics? Let's see the definition on the slide. Statistics is the collection, grouping, systematization, presentation, analysis, and interpretation of data or results of observations. Or we can say observation results. So, where can we use statistical methods in general? In our life, in your student's life, or in your practice maybe? If we talk to you specifically about our situation, that is medicine in general, statistical methods are used to, where? Firstly, the study of public health and the factors that determine it. Second, the analysis, evaluation, and planning of medical care. And the last, special scientific research, or we can say clinical trials. Also, statistics is a section of mathematics. I think you know this. Statistics based on the mathematics, and this is the section of mathematics. Mathematical statistics, or if we say about our situation, we can say medical statistics, yeah? We are in medical university. Mathematical statistics works with numbers, really, with numbers. And so you and I will need formulas and numbers, and even those data that are not expressed in numerical form, we will try to translate into quantitative numerical data. And as a branch of mathematics, statistics studies general populations and their variability. So, what is the general population? Or we can say population, yeah? General population is a Russian term. I think in English language literature, it's a population. In our country, it's common to say general population, and in my lecture, I will say general population or population. So, general population is a set that includes all the data, phenomena, objects, or people that are being studied. For example, we want to conduct a study on whether freshman in a pediatric university know physics well. We can say, yeah, freshman is a first-year student, yeah? And in this situation, the general population or population would be all first-year students at pediatric university. So, that is, the general population could be, for example, all children with type 1 diabetes. If we want to conduct some kind of study of the drug risk factors, it can be all men of a conscription age. It can be people who live in a certain region, yeah, for example, people in St. Petersburg, or people in, I don't know what else, so in Moscow, in other countries, in other area, for example, yeah, for example. It all depends on the purpose of the study. So, it's impossible and sometimes very expensive to study the whole general population. So, statistical methods are used that allows us to draw conclusions about the whole population based on studying a sample from that population. We are not studying the entire population, but only a small group, sample from this population, that is, a portion of elements that are somehow selected from the entire full population, yeah? And what is about sample, yeah? Is a part of the elements selected from the general population. So, what is about the sample, yeah? Sample must be representative. It's very important, really. Firstly, the sample must be representative. Non-representative sample we can't use in our practice. So, what does that mean? What is about representative sample? It must be chosen at random and must have the same structure as a general population. Yeah, we must take this sample, representative sample from population, and it must have the same structure as a general big population. If we discuss the freshmen or first-year students, yeah, in our university, example again, yeah, you and I can't just take dental students for the study, because then that sample would not show the real structure. For example, we have all different students, yeah, and for example, we can take only unrepresentative sample, yeah, for example, only dental students, and this sample would not show the real structure of all population. There are other students in the university besides dentists, yeah? And the result that we will get by studying only dental students will not allow us to draw a conclusion about the first-year student in university. And again, let's look at the figure, yeah? This figure shows the treatment majors and dentists, yeah, all students. If we take a small fraction of dentists with you, it will be a very small sample, and it will not allow us to generalize to whole general population, yet it will be unrepresentative sample. For example, if we take only the medical specialists, all other, yeah, the sample will be also unrepresentative because it does not reflect the entire structure of our population, yeah, how I said. So, for example, very small sample. Very small sample. For example, only one group. Or, for example, only 10 students, yeah, for example, only one student from one type of, yeah, or for example, from the dentist, one from therapist and other students, yeah. And it does not reflect the entire structure of our population. The university has the most pediatric students, which means that for our sample, we should take the most pediatric students. And we should not forget about all the other majors. Yeah, for example, biophysics students, medical and preventive medicine students, dentists, for aging groups should also be reflected in our sample. And the very interesting question. How does the selection happen? How does the selection happen? The selection happens randomly. Yeah, I said earlier that the selection must be happens randomly. That is, we don't look only for students who were excellent in physics in school to get some results that we want. We must choose randomly and try to make sure that we have the same structure in the general population. It will be a representative sample, yeah, for example. We can see on this picture, on this scheme. So, and now we have made the sample. We have made the sample. We have made the representative sample from population. So, next, what should we get as an output. What are we investigating? In clinical trials, we usually have two possible outcomes. Firstly, it's clinically significant condition or event. That is, recovered, not recovered, for example, quality of life improved or not, and so on. And the second type, what? When indirect criteria for assessing the outcome are evaluated. We compare laboratory indicators, for example, data from instrumental studies. The outcome, for example, can be a decrease in blood pressure by any number of millimeters of mercury. We can compare lab values. It's our outcomes. Many different outcomes maybe. And next, what kind of clinical trial designs can we have? After that, we must think about designs. So, there are primary and secondary studies. There is the primary research or studies and secondary studies or research. Of course, it all starts with primary studies. Firstly, we must do primary research, primary studies. What is this? So, let's look at the diagram on the slide. We can have clinical trials that are maybe experimental or observational. What is about experimental clinical studies? There are studies in which there is some kind of intervention. For example, it could be some kind of treatment or some kind of procedure and operation. And here we can have two options. Experimental studies may be controlled or uncontrolled researches. Most of the time, we need to do controlled trials, which means we need a control group. That is, we compare the effect of the treatment with the effect of the intervention in the control group. Control group can be either a placebo or some already known treatment, a known drug, for example. And the experimental group is our new treatment whose effectiveness we want to test. And the members of the experimental and control groups must be comparable in all respects, except for the treatment. Everything else must be the same. Approximate age, approximate gender distribution, stage of the disease. We can't use or it's impossible to take two groups for comparison, where one, for example, has a mild type of the course of the disease, and other group has a severe type of course of the disease, for example. And or we can't compare children's and grandmas, for example. It's not representative. We can't use these types. The groups should be comparable in all respects, except for the treatment or type of procedure performed. Group segment can be random or randomized or non-randomized. What is about randomized? Randomized or not? We can say randomized or non-randomized controlled studies. Next, it was experimental studies. What is about observational studies? They don't involve any intervention. Events are given a natural course, and they observe the course of the disease, the factors that influence the disease. And descriptive research is when we just describe some cases. Observational research may be descriptive, and analytical. Analytical is we study some relationships For example, to identify or measure risk factors of the disease, assess the impact on health of some practical actions. That's an analytical study, analytical study. Their analytical studies may be cohort, case control, and cross-sectional studies. All of these studies are summarized by systematic reviews and meta-analyses. These are secondary studies. They are based on primary studies that have been already done. The person who does a systematic review or meta-analysis is not doing the study himself. He is analyzing already existing published or unpublished studies. These people can analyze studies which other scientists did earlier, for example, analyzed using mathematical statistics. So now, after this, after the designs of our trials, of our clinical trials, we must talk to you more about randomized trials. And now, because nowadays it's the gold standard, when a study is randomized, especially double-blind. I think you heard this word earlier. And what is about study? And randomized clinical trial is a study in which patients are randomly assigned to treatment group this is randomization procedure, and are equally likely to receive the study or control drug, comparison or placebo drug. And these studies may be open and closed. An open study is a study in which you know who is in which group, and it's a lower level of evidence. It's better when the study is blind or double blind, and if double blind is not possible, a triple blind study is used, where the outcome of intervention is evaluated by a third person who does not know which intervention was done. Also, studies can be single center, when there is one clinic, and multi-center, when the study takes place in several clinics, maybe even in several countries. We can take patients, we can take studies, we can take practical using from different clinics. It's multi-central, part. So, studies, multi-center studies. This will all allow us to increase the sample size and get the number of patients needed for the study faster, really. If we sketch out these studies, we have a representative sample that is randomly selected from the population, or we can say from the general population. Then we randomly divide it into a core group and control group, main and control group. How can this be done? The easiest way, for example, is to select even-numbered patient into one group and odd-numbered patient into another group. And first patient one group, second patient second group, third patient one group, the fourth patient second group, and etc. So this is when the study is open. But if the study is blind, the allocation is done the random number tables. Envelopes are sealed after allocation. No one knows about this allocation. The studies are encrypted or computers, and there have been so many precedents of these envelopes being stolen to figure out who is where and to change the results. It's very badly, there have been attempts to break computer cybers. But serious research is now very well protected. After we have assigned the cohorts, we evaluate two different outcomes after treatment in the main group and in the control group. After this. After after we have assigned the cohorts, this study, we must evaluate the different outcomes after treatment in main and in control group. So let's now consider a cohort study with you. What is this? Firstly, say the definition that the cohort study is an observational study, not an experimental study, meaning we don't have any intervention. It simply selects a group of patients and studies them over time. The purpose of a cohort study is to investigate the risk factor, prognosis, and development of disease. The most famous cohort study is the Framingham study. I think you heard about it, which was conducted in United States. It began back in 1948 and continues to these days. And more than 5,000 people are under observation, Framingham study. So, risk factors for coronary heart disease are being studied in this study. Gradually, more and more new data is emerging. Time is going because, and medicine is not staying, on the one stage, So, it began with the fact that the risk of developing the disease increases with age. Then smoking is associated with an increased risk, diabetes mellitus. Then, by the end of the 20th century, many genetic loci associated with the major risk factors were discovered, The research is long, which identifies more and more new risk factors. And if we sketch out the study, we have a sample of patients that we are monitoring. And there are those who are exposed to risk factors. They may or may not develop the disease. And those who don't have the risk factors, but they may or may not develop the disease. And this method can be used to calculate the relative risk of developing or not developing the disease. You can see the scheme on presentation, on the slide. So, and now, next, we said about control analytical studies. Next is case control analytical studies. Let's see. Let's talk about it. About case control study. The purpose of this study is to compare the characteristics of a group of patients with a particular disease outcome called a case, it's a case, to a group of patients without an outcome called a control, to determine how much more, less often, any factors occur in this case than in the control. So, It's a bit of an inverse pattern, yeah? While cohort studies are more often prospective, we can say long-term, they are rarely retrospective. Then, case control studies are retrospective. That is, the effect of a factor was in the past, and we are evaluating it now. For example, we have a case group of women aged from 50 to 81 years old with a hip fracture, and control group of women of the same age without hip fracture. Yeah, you can see. So, the factor here is talking hormone replacement therapy. Yeah? Значит, case. Woman with a hip fracture. Control. Woman with the same age without hip fracture. And the factor, taking hormone replacement therapy. Accordingly, if we look at the chart on the slide, on this chart, in the case group with the hip fracture, there were those who were taking hormone replacement therapy, and there were people, women, those who were not taking it. Yeah, and in the control group, there were also those who were taking and those who were not taking hormone replacement therapy. And in this case, you can try to estimate the odds, like what is the chance that hormone replacement therapy affects hip fracture at that age. And this study was done in Sweden. And it showed that taking hormone replacement therapy reduces the risk of hip fracture at that age. And now we can see that all kinds of studies add up into a pyramid of evidence-based medicine. By level of evidence, the closer to top of the pyramid, the higher the level of evidence, the more we can trust a given study. At the lower level, let's see at the lower level, it's just some expert opinions, comment and expert opinions. So, like, for example, I'm a doctor and I said something. On the whole, it's unreliable. Then the case series studies, case study series. Then case control studies, cohort studies, randomized controlled trials. And at the top are systematic reviews and meta-analysis, that is, when several studies are summarized. Logically, it's logically. And at the top are systematic reviews and meta-analysis, and some words about it, There may be situation, for example, where one sample of studies have one result and another sample has different results. In some ways, they overlap, and in other ways, they don't. All of the lower levels of the pyramid are also important for us. All of these are important because they allow us to propose a new hypothesis. For example, we investigated a series of cases and obtained a new hypothesis that needs to be tested. Based on this new hypothesis, we select a new sample and think about the research design and what we want to get out of it. Once we have the results, we can already summarize them into systematic reviews and with or without meta-analysis. It may be or it may not be, for example. Now, or once we have the results, we can already summarize them into systematic reviews, yeah? And our task now is to learn how to do our own small studies in small, simple samples. This will come in handy and in all other departments when you do small studies. Yeah, really. So, and to choose the right research method, we need to know the classification of samples, yeah, and the classification of data. There are independent and dependent samples. Yeah, samples may be independent and dependent. So, independent samples are samples where the probability of selecting any subject from one sample is independent of selecting any subject from another sample. They are completely different people. For example, we received children with celiac disease into the first group and children without celiac disease into the second group. They don't overlap in any way. They are completely different children. These samples are independent. And what is about dependent samples? Dependent samples are samples where each test taker in one sample is matched according to a certain criterion to a test taker from another sample, or the same test taker in a repeated measurement. For example, they are subjects before and after something, or we study the same patient in different ways, or two different time points. For example, the first group in children with celiac disease at the time of diagnosis, and the second group is those same children with celiac disease after 1 month of following a gluten-free diet, for example. And these samples are called dependent samples. So now, let's take a look at data. Data can be categorical and quantitative. Yeah, I said that to research, to choose the right research method, we need to know the classification of samples, about we said earlier, and classification of data. So, let's look at data. Data can be categorical, qualitative, and numerical, quantitative. So, let's look at the table, at this table on the slide. So, qualitative, categorical, qualitative data can be nominal and ordinal, or rating and categorical, you can say. In a nominal rating data, categories are mutually exclusive and not ordered, meaning you can't be in two categories at the same time. And the categories are not ordered. This does not mean that any one category is better or worse than another. An example of such data would be gender, blood type, marital status, We can't say that being male is better than being female, or being married is better than being single. The categories are mutually exclusive and unordered, And that is either this or that. In ordinal data, rating data, categories are mutually exclusive and ordered. For example, stage 4 cancer is worse than stage first, than the first stage. More importantly, statistics as a branch of mathematics works with numbers. or maybe situation, or the third degree of hypertrophy is worse than the first type, And more importantly, statistics as a branch of mathematics works with numbers. So it's very important to code categorical data, that is, to put them into a digital format, For example, gender may be 0 and 1. Maybe 0 is male, 1 is female. Blood type, we know that there are 4 blood types, first, second, third, and fourth. Marital status, maybe 1 is married, 2 is single. And ordinal data, also digitized, for example, stage of illness, death scale, and it's categorical, for example, and so on. It's either with coding here, but you have to do it. We can't work with the letters M and F, for example, or with the words weak, very weak, strong, and so on. We have to encode them. Numerical data, quantitative data, on the other hand, are discrete and continuous. So, discrete data only take integer values. For example, the number of sick days per year, the number of patients in the department at a given time. And what is about continuous data? Continuous data can take any value within a given interval. For example, height, pressure, temperature, body weight. Very interesting with age. In fact, age is a continuous variable, And we get older every day, and we can be 20 years and 3 months and 2 days. So it's a continuous variable. But it's inconvenient to work with it in this format, and we always calculate age in full years, so it becomes a discrete variable, quantitative discrete variable. Let's continue, to talk about mathematical statistics. And at the beginning of any study, there is preliminary analysis of data. Preliminary analysis. And we figure out what the data are, and qualitative or quantitative. We figure out which samples are dependent and which are independent. Then we start doing preliminary data analysis, which is graphing the data and calculating descriptive statistics. Let's break down that descriptive statistics exist. That is, how we can describe the sample we have. We describe measures of central tendency, the sample mean, mode, and median, and we estimate measure of range, the interquartile range, the variance, and the standard deviation, variance or dispersion, we can say. Let's break down each of these descriptive statistics in detail with examples, with examples, especially with examples to understand, to best understand to you. So, what is about the sample mean or sample average, we can say? This is the arithmetic mean of the trade in the sample. So, you can see the formula on the slide. That is, it's the sum of all values in the sample divided by the number of all elements in the sample. For example, on the slide you can see the example. This is a score for an exam in a group of 10 people. We added up all the scores and divided by 10. How much scores was, And you get an average score of 3.5. For example, 10 marks. we must remember, what is about sample, so average value, mean value of this. How can we calculate it? We must take all marks, summarize it, and divide by how much numbers was, and after we have average score. Now in this example we have 3.5. It was the sample average. What is about the mode? The next statistic is mode. Mode is not just about mode in statistic. The mode is the most common value in the sample. In our case on the slide, the mode score is a 3. Better would be excellent, For example, the mark for an exam in a group of 10 people, the most frequent value is mark 3. I think you know that better would be excellent, will be mark 5, for example. That is the most common grade of 3 for an exam in a group of 10 people, mark 3. This is a mode. If we have a continuous data and we construct a distribution function, then the mode will be that value of x at which the probability density takes the maximum value. Yes, there can be bimodal or multimodal distributions. That is, when there will be, for example, 2 maxima. This is most common when there are 2 distinct groups in the population, such as men and women. Men have a mode, women have a differently. For example, men have one mode, women have different mode. Women, we combine them into one population. That can happen too. So, and what is the next descriptive statistics? This is median. From school, you should remember the median of the triangle. What is about median of the triangle? It divides the side of the triangle into 2 equal parts. Into 2 equal parts. So, does the median in statistics? What is about median in statistics? The same idea. The median divides an ordered sample into 2 equal parts. Ordered sample from the smallest to the largest. This will be the center value of the ordered sample. Let's look at the example on the slide. An exam grade or mark in a group of 9 people. To find the median, we must order the sample in ascending order, and the value that will stand in the middle, that is, divide the sample into 2 equal parts, will be median. You can see. In our case, this is the value of 3, 4 number less and 4 number more. It's the center of this sample. So, the median will show us 50% of the values greater, how I said, than mark 3, and 50% of the values less than our median. In our example, it's mark 3, And the median shows that 50% of values are less than the median, and 50% of the values are greater than the median. It's convenient to use when the sample does not have a normal distribution. For example, the average wage at a company. Does the median wage correctly reflect the average wage of the average person in the entire enterprise. Of course, it doesn't. Yeah, really. And there are high-paid top managers, for example, and middle and junior staff. And of course, the average wage, money which they take, and maybe higher to top managers, than the wages or than the money of most employers in the enterprise. It's more convenient to use the median to characterize the central trend, because it will show that 50% of the people are paid more than that amount, and 50% of the people who are paid less than that amount. So this will already be a more realistic wage, realistic money, which people take in this company, for example. When the sample has an odd number of items, as we looked at with you in the example, that's understandable. But what if the sample has an odd number of elements? In that case, we take the arithmetic mean, for example, arithmetic mean of the two center elements of the ordered sample. Again, we divided the sample into two parts, and the center there are two values. To calculate median, we take the arithmetic mean of the two center values of sample. So 3 plus 4 divided by 2. This median is 3.5 of this sample. What is about next important concept? Next important part, descriptive statistic. It's percentiles. What is about this? The percentile of a distribution is such a number xp, that the values of the p part of the population and less than or equal to xp, with index p. For example, the 25th maybe what types of percentile? 25th, 5th, 15th, and 75th percentiles are most commonly used. What is about the 25th percentile, also called the bottom quartile? Is such a value xp that 25% of the variable is less than that value. What is about the 50th percentile, also called the QQ quartile or median? Is the value xp that shows that 50% of the variable is less than value. And last part is the 75th percentile, we can say upper quartile, Q3, is respectively the value below which 75% of the variable values fall and 25% of the values are greater. Conventionally speaking, we have divided the sample into 4 parts. For example, on the slide, the test scores of a group of 15 people. Marks, we ordered them in ascending order and divided the sample into 4 parts. First, second, third, and fourth. The one is the middle, is the quartile Q2 or median. This is, which means 50% wrote a test score of 33 bells, or less, and 50% wrote the test score greater than this ball, yeah, more than 33. The lower quartile Q1 is respectively. We divide a lower part, yeah, this lower part of the sample in half. Here we divide the lower part in half and the lower quartile Q, yeah, 54 balls, yeah. And it turns out that 25 people wrote the test less than this mark, yeah, these points, and the other 75%, these 75% of people who wrote the test more than 54 points. And the top quartile Q3. We divide the top half, this top half, into two parts, divide, and it turns out that the top quartile is 89 points. What does it mean? This means that 25 of people who wrote the test more than these points, these numbers, yeah, this part, 25% from all samples, yeah, and 75%, these 75% of people who wrote the test with less than 89 points. 89 points. Again, yeah, you can see about quartiles, yeah, again. Firstly, we find the median, the second quartile. It divides our sample on two parts. And we can say that 50% wrote the test on more than this value, yeah, more than these points. This is 50%, and 50% less than this point, yeah, than this mark, for example. What is about lower? What is about lower quartile Q1? It divides lower part in half. So this is lower part. The center of lower part is lower quartile Q1, and it divides the lower part on the sample in half. So, and we can say that 50%, 25%, yeah, we can say 25% from all group wrote the test on mark less than 54 points, and these 75% has a mark more than this 54 point. It's low quartile. And about upper quartile, yeah, Q3, or top, or we can say top quartile. So top quartile is the center of upper part, yeah, and it divides the sample on what parts. 75% has a mark less than this then these points, and 25% of people, from all people, yeah, write on the test on more than this point, more than this mark, for example. This is about percentile and quartiles information. So next is interquartile range. And we can use interquartile range like as a measure of dispersion. The interquartile range is the difference between the upper quartile and the lower quartile, that is Q3 minus Q1. In our example, the same example, it's Q3 89 points minus Q1 54 points, it's 35. Would be 35. It's interquartile range, for example, yeah. And what is the next? Centiles are very important, yeah, in pediatrics, yeah. on the percentiles, percentiles. And pediatric doctors use the centile tables all the time. Centile tables. There are very, very different centile tables. And pediatric doctors use these tables all the time. On the slide is a centile table for the height and weight of a girl under age 1. This data is compiled for a very large group of girls distributed by percentiles. It turns out that 3% of girls are born less than 45.8 centimeters tall and so on. For example, first interval, 3% says us that 3% girls are born less than 45.8 centimeters that tall and so on. The interquartile range is highlighted in purple, which is the norm. You can see purple color. Centile intervals are assessed when a pediatrician doctor examines a child under 1 year of age at certain period, measures height and body weight, and looks at what centile intervals the values fall within. If the values fall into interval 4 on 5, you can see and it indicates normal development of the girl, if we say about girls. What is the next? And on the last lecture, we said about dispersion, and today we must say some words about it too. And it's already familiar from our last lecture. You could see this information on last lecture and heard information. We already told you that the variance and dispersion is a measure of the spread of a random variable or a measure of a deviation from the mean. This slide shows the formula that you will be using in your statistics class, And I said on last lecture that on the next lecture will be special formulas, which we will use in our practice lessons. This is. So, and the sample will be small. I think you know that the sample will be small. And 25 people, so you will use the refined formula. For if in our practice lesson will be 25 people in the sample. And we can say that this is a very small sample, and we must use the refined formula when we divide by not n, how much number in our sample. We must divide it by n minus 1. So, and let's look. This is information, about formula of dispersion or variance, sample variance. So, let's look at the example. Let's see the example and how variance is calculated in practice. In the example, we see the grades for the exam in a group of 5 people. Mark 2, Mark 3, Mark 3, Mark 4, and Mark 5. So, first we count average. We get 3.4. How can we calculate the average value or mean value? Summarize all numbers and divide by how much numbers was in our sample. Calculate it. It's number 3.4. Next, we count the deviation from the mean. We subtract the mean from each. So, number minus average put into the deviation, and the same, and the same. The same calculation, not same number, same calculations. Then we square the deviation and this deviation, put in square, and take the sum of the squares of those deviations. This number plus this plus this plus this plus this will be 5.2. Since the sample is small, we must divide it by what? By n minus 1. So this summarize, we divide by 5 minus 1, yeah? Because our sample is small. The numbers in our sample less than 30. So the sample variance of this sample is 1.3. The sample variance is 1.3. Another example. Consider two groups. The average score for both groups was 3.4. You can see. Average number is this, average value is the same. 3.4. So, but the first group had a variance of 1.3. But the second group had a variance 0.3. That is, in the second group, all values are closer to average, while in the first group, we have more variation in values. There are also scores of 2 and 5, different scores. The smaller the variance, the closer the value is to the mean. The greater the variance is more scattered. The values are from the mean. Don't forget about it, yeah? We can compare these points. So, we must remember with you that the sample variance is measured in square units. I said this information on my last lecture. And this is not very convenient. So we use the standard deviation. Yeah, this is a joke of mathematics. Put in square, after that have a root. So, and the standard deviation is also a measure of the spread of a random value. It's calculated as a root of square, of the variance. It's used instead of the variance when it's necessary to estimate the scatter in the same units as the data itself, the letter is, this is a sigma, this is a Greek letter, name of this Greek letter, sigma. Sigma is standard deviation. We can calculate it. Take root of what? Root of D, our dispersion or sample variance. Root of our sample variance. So, the next important concept is the confidence interval. Really important concept. The confidence interval is an interval of values that includes the estimated general parameter with a specified probability. Let's understand what this means. Let's look at the scheme. We have calculated a sample mean value of x with a dash, for example. And we want to generalize the result to the entire population. The confidence interval allows us to answer the question of how likely the general average or the mean value of general population will lie within that interval. The first calculate the sample mean and then look for delta x, which allows us to estimate the limits of the confidence interval. This is our margin of error. We can say that with 90%, 95% or 99% probability, as we decide, the mathematical expectation of our random value in general population will lie within this interval, lie in this interval. Or if we draw another sample from that population, Then with some probability or new sample mean will lie in the same interval, that same interval. The character is probabilistic, but it also allows us to infer from the sample to the general population. This half-width is calculated by the following formula, where sigma is a standard deviation, what is about n is sample size, and what is about t alpha n. This is a table value. The name of this value is the student's ratio. It depends on alpha, which is the probability of error that we are laying down, 10%, 5%, or 1%. And n is the sample volume, how much, numbers in our sample. And the result is usually written down as follows, writing down as follows. Is the mathematical expectation of the random variable in general population equals the sample mean value or average value plus minus delta x. And what is about x? That value of the half-width of the confidence interval that we calculated. Now there are requirements in publications not to write plus minus, but to write it as follows, E minus delta x or average plus delta x. So now the question is which to choose, 90%, 99% or 95%. On the one hand, we want to narrow the interval so that it's small. So it seems to us that we have made the calculations more accurate, if we take the 99%, for example. The confidence interval will be narrower if we increase the sample size. But if the sample has a small variance, there is not as much variation in the data. These two would allow a more accurate confidence interval to be calculated, but the confidence interval decreases where if we decrease the level of confidence needed for a general average. In the example, in the figure, we see the narrowest 90% confidence interval. This means that there is a 90% probability that the general average will fall somewhere in this interval, in here part. So, but here the 10% is the probability of error. The widest is the 99% interval. We increase the accuracy, and the interval immediately widens. For example, to take the example of shooting at a target, the bigger the target, the higher the probability of hitting it, and the smaller the target, the lower the probability of hitting it. The same is with the confidence interval. The narrower it is, the less likely it's that the general average will hit it. The wider the interval, the greater the probability, 99%, that the population mean will be in the interval. In medicine, 95% confidence interval 95% is used. The margin of error is 5%. It's for medicine. It's really for medicine. So Let's move on to a graphical representation of the data. We have described our samples, calculated all the descriptive statistics, and now do a graphical representation of the data. What is the purpose of graphical representation of data? First, for clarity. Describing with words is one thing, but when we see the graph, it's more convenient. And it's also used to recognize structure and highlight any distinctive features of data. Outliers. There are extremely high or extremely low values. Areas of clumping. To detect errors in the data, we could lose some numbers. For example, on the graph, it will be clearly visible. Or to detect any new phenomena, maybe. Any new phenomena. So, let's go over the basic graphs and break them down. Frequency distributions are more conveniently just depicted by a pie chart. If we have one group, we can see the distribution by gender, for example, male and female, yeah? When we have one group, for example. If there is more than one group, it's better to use an intra-column chart. Let's say the example, for example, women and men. We see that there are more women, and we also see the distribution of irritable bowel syndrome, for example. So, women have about 50-50 split of irritable bowel syndrome with diarrhea, or with constipation, and men are dominated by diarrhea. Yeah. So, the next frequency used chart is the histogram. Really, histogram. And frequency distributions are more conveniently depicted by a pie chart. Histogram. What is about histogram? The histogram is a set of adjacent rectangles with bases of equal length. The width of each column corresponds to a certain interval or variable values. They are the same width. Yeah, same width of every column, yeah, of this, we can see. So, the area of the column is proportional to the frequency in that interval, yeah? We must remember this. The next example is scatter diagram. This is a very handy diagram. Each point on this chart is one sample item. The number of points are placed in a Cartesian or coordinate, yeah? And show values for two variables. For example, height and birth weight. Let's see, yeah? And look, we got one value knocked out. What is it? An outlier, error, mistake. We need to analyze it. It happens that children are born with an extremely low birth weight, yeah? Really, for example, if we see. Extremely, yeah? Really less than 1 kilogram, yeah? So, then the height would also be correspondingly small. Then it would be considered an outlier. But in our situation, the very low birth weight of over 45 centimeters, yeah, that C is clearly an error. Such a patient should be excited from our study because we have no patient with weight less than 1 kilogram and height more than 45%. 45 centimeter. Each mistake, yeah. Really. And the graph allowed us to find the error in the data. Yeah, really. We can also conclude that there is a positive relationship between the variable here. As one variable grows, so does the other variable. So, the next frequently seen graph to describe the data is the mouse touch box graph, or we can say box and Vickers chart. It visually depicts the distribution in the sample. The median is also shown, and you can also draw the mean if you want. The median divided the sample into 2 equal parts. Median. And the bottom boundary of the box is the bottom quartile. The top box boundary is the top quartile, yeah? Lower and upper, top and bottom. The upward Vickers is the top quartile plus interquartile range and a half. And the interquartile range is the difference between upper and lower quartile, how I said earlier. The box and Vickers chart, this chart, yeah, is lower quartile minus 1.5 interquartile range. Sometimes it is found that the Vickers are the minimum and maximum, but modern computer programs give the interpretation of this box, which is why you and I are parsing it. Values greater or less are drawn with separate dots. These are outliers, we can say. So, the graph is handy when comparing 2 samples. Group 0 is newborn without hypertrophy, this group, and group 1 is newborns with hypertrophy. Without dividing by severity of fact or the fact of whether there is a hypertrophy or not, we can see that hypertrophy mass is much less. There is also an ejection. One value is very small for this sample is ejection. You can clearly see that the samples are different from each other, really. Also, an error bar graph is used to compare 2 samples, error columns, we can say. And it shows the mean value and the 95% confidence interval. You can also see that there are very strong differences between the groups, really, and about 0 and first group, yeah, or with hypertrophy. And in what case to use which with graph is the topic of the next lecture, yeah? We will talk about it on the next lecture. So, this brings us to the essentials, yeah? And how can we recognize our essentials, yeah? All research begins with a hypothesis. Based on our hypothesis, we think about the research design. Based on the hypothesis, we calculate the sample size. We recruit the sample. First, the hypothesis is what we want to get out of our study. When we have and when we have thought the study design, recruited the sample, describe the sample with right method. Descriptive statistics, we said about it earlier, and visualized it graphically. Then we proceed to test the hypothesis, whether we are right or wrong. In statistics, a statistical hypothesis is any assumption about numerical values and distribution functions. It sounds scary, but it really isn't. The hypothesis we are testing is called the null hypothesis. For example, the mean value of the parameter in two general populations are equal or differ insignificantly. So our procedure had no effect on the indicators. As there was a mean value of hemoglobin after treatment, it became approximately the same. That is, our treatment was ineffective or ineffective, And we had a hypothesis that our new experimental treatment was effective in treating anemia. Low number of hemoglobin. The alternative hypothesis is the hypothesis when the mean value differs significantly. That is, our treatment was effective. And the null hypothesis is always that we are ineffective when the mean values are equal, and alternative hypothesis can be opposite hypothesis. That is, the mean value are not equal to each other. There may be an alternate hypothesis when, for example, after treatment, the index increases, become more, or vice versa, decreased, became less, for example. So, and how do we test our hypothesis? How can we do it? We test it with a statistical criterion. Statistical criteria is a rule by which the null hypothesis is accepted or rejected. Criteria can be parametric, how you can see in the table on the slide, or non-parametric. We can use parametric criteria only when our data are quantitative. Only when there is a normal distribution law in our population, and only if the variances of two samples are not very different, or the variances should be about the same. In all other cases, if we have qualitative data, or our sample has unnormal distribution law, and difference between samples is the most, and what is this in these cases we must use non-parametric criteria. Why do parametric criteria exist after all? Why don't we use non-parametric criteria everywhere? No. When the condition is met, we absolutely must use parametric criteria because they are more powerful. Let's break down what the power of the criterion is. We said that these criteria are more powerful. And what is about power of the criterion? The first, we need to understand what kind of errors there are in hypothesis testing. Let's look at this example. The null hypothesis is that the patient is healthy. It can be true that the patient is in fact healthy, really healthy. It can be incorrect and the patient is sick. We can also accept and reject our hypotheses. There are 4 possibilities. Really, there are 4 possibilities. 1, 2nd, 3rd, and 4th. Let's see. We can accept the correct hypothesis. We assume the healthy patient is healthy, really, and all is well. Healthy is healthy and it's good. It's well. This part. It's not error, yeah? We can reject the correct hypothesis. That is, we take healthy patient as the sick patient. We have a hypothesis that the patient is healthy. We reject it, and the patient is actually healthy. That's mistake of the first kind, this point. And yes, it's a mistake, but it's not that critical. We'll schedule a follow-up study and find out that our patient is healthy really and everything is fine. But maybe the hypothesis is wrong. The patient could be sick. Here, if we reject the null hypothesis that the patient is healthy and the patient is sick, we get it right. We take the sick patient as the sick, we treat him, and everything is fine. So, but what if we accept the wrong hypothesis that sick patient is mistaken for the healthy patient? That's not very good. We would be making a mistake of the second kind, this part. That's a more serious mistake. We can't simply reduce both of these errors at the same time, only by increasing the sample size. And if our sample size is fixed, then by reducing one error, we will increase the other error. We don't always have an opportunity to increase the sample size. Sometimes the disease we're studying is very rare and we can't get a large sample. This is where we have to make a compromise. If we try to reduce error of the first kind, that is, reject the correct hypothesis and take a healthy patient for a sick one, we don't go around committing error of the first kind. We will be less likely to mistake patients for the patients who are sick and will be fine. But by doing so, we might miss a really sick patient. That is, we might mistake a sick person for a healthy person. Then we would have an error of a second kind, which is not very good. So, a visual picture on the slide that depicts the first kind of error is to reject the correct hypothesis when we mistake a non-pregnant person for a pregnant person. Yeah, we can say mistake of the first kind. We say the man, you are the pregnant. Yeah. Really, it's not can be, yeah. Error on the second kind, when we accept the wrong hypothesis, when we explicitly tell a pregnant woman that she is not pregnant really in this situation. The probability of making an error of the first kind is called the significance level alpha. The probability of not making an error of the first kind is first alpha confidence level, yeah? One minus alpha, confidence level. The power of the criterion is the probability of not making an error of second kind. Parametric criteria are more powerful, we said, yeah? As you and I have said, If it's possible to use them, we should use parametric criterion, because when we use them, there is a higher probability of not making a second error. What are the approximate values? When we say we can't simultaneously reduce these errors without increasing the sample size, the significance level is taken to be 0.5. That is 5% probability, 0.05, that is 5% probability of an error of the first kind is considered acceptable. The confidence level in this case would be 95%. This is an absolutely normal value. The normal acceptable power is considered 80%. In medical research, the significance level is taken as 0.05 or 5%. The confidence probability is respectively 95%. The power is 80%. So, our algorithm for hypothesis testing will look like this. Firstly, we must choose a criterion. We choose the criterion based on the hypothesis we want to test. It may be a hypothesis of distribution normality, and it's necessary to check it, because on this basis we will need to choose parametric or non-parametric criteria. Accordingly, the criterion will depend on the type of distribution, on the type of sample, on the number of groups being compared, 2 groups or more than 2 groups we are comparing. If the criterion is chosen incorrectly, our results will have very low validity. That is, we will not be able to generalize them to our general population. We have analyzed the data, the hypothesis, the type of distribution, and selected the criterion. Each criterion has its own algorithm for calculating criterion statistics. Let us denote it by Q. We then compare this number Q with some critical values. In medical researches, we take the level of significance alpha is 0.05. We can take a more exact one, 0.01, so we get 5% in and 1% of error. Let's represent this on a coordinate line. You can see it on the slide. We have some tabular value here. There are tables for each criterion. You will use them in practical exercises. We label these critical values and compare our control value Q, which we calculated according to a certain rule for a certain criterion. If it is in the area on the left, we have no reason to reject the null hypothesis. And this is the area of insignificance, this area. So, if the control value is less than the critical value, then we say that we accept the null hypothesis. So, distribution is normal or mean values in the populations are equal. If our control values falls within the mean region, this is the region of significance with 95% confidence level, this part. Here we already reject our null hypothesis and say that our mean value is different with a 95% confidence level. That is, with 95% probability, these differences are not random, and they really are. If we are lucky and our value lies on the right side, this side, then we say that the differences are statistically significant. That is, we accept the alternative hypothesis with a 99% confidence level. If the control value of the criterion is greater than the critical value at alpha equal to 0.01, then we say that we accept the alternative hypothesis with 99% probability. With 99% probability. And it was only small part of mathematical statistics, which we said today. On the next lecture, we continue to talk about statistical criterion and mathematical statistics in medicine. How we can use it, where we can use it, what we should to use, And so, today I can say you thank you for your attention and goodbye.